So our project is on TensorFlow and higher order functions by Daniel Grusov, Tyler Mull, and Kevin Jacob. TensorFlow is a Google-developed open source machine learning tool that helps facilitate the production of neural networks. So what TensorFlow does is compress really complicated data structures and linear algebraic computations into a really compact and easy to interact with library. So you can use TensorFlow for a lot of things, but it ranges from detecting different diseases, identifying pictures, or moderating a chat room. So this is the basics of machine learning. Basically, you have these small nodes that contain different values composed in different layers. So in the input layer, if you were processing a picture, each node would correspond to a pixel in the picture. And each of the hidden layers maintain a certain parameter, like basically a percentage. And after each computation, the results are fed through the layers and are outputted in the output layer. So if, for example, you were trying to identify whether a picture was a cat, the input layer would be the pixels in the picture of a cat. Hidden layers would be different ways of processing those pixels, and the output layer would be a true or false Boolean. Depending on the way that you're processing this data and the different framework for learning, you could have a signal that propagates through the layers backwards and adjust the parameters to better fit the picture. So if you had a cat picture and it identified it wrong, you could send information backwards through the layers to say that it actually was a cat picture and adjust the parameters to make it work better in the future. So a convolutional neural network is an example of a neural network, and it's basically where you extract relevant parts of an image to lower the amount of data you have to process, because neural networks, once they're layered, can grow exponentially and require a ton of computing time. So for a convolutional neural network, you start with a picture, take the relevant features, which is called pooling, and you take the results of the pooling and you do a little bit of data processing that basically assigns each feature a weight, and then that process is repeated until basically the model can predict what the picture was of, which is really cool.
So how does this all work? So each individual node is basically its own linear regression model. It's composed of data, weights, and a bias, as you can see right here, that then when it gets summed up, gets formed into an output similar to the Booleans that Tyler described earlier. Now all of this culminates into a cost function that is trying to minimize it in order to maximize correctness for a given model, which, if you remember your concepts from Calc 1 for optimization, this is pretty similar to that. We're trying to converge to where the cost function is at its minimum. Now, this is a simplified version with individual inputs and values, but this could be expanded with tensors, which are generalizations of sets of algebraic objects. So a 1D tensor would be like an array, a 2D tensor would be a matrix, and a 3D tensor would just be called that, a tensor, which gets abstracted out to the generalization. And they're extremely useful to develop large networks for TensorFlow. So our model basically uses this to take handwritten numbers and translate them into images, which we'll demonstrate now. So looking at our code, we have first import TensorFlow into our Python code in Jupyter Notebooks. We then get our data set of images. So this is basically a set of written numbers that the computer will then interpret, or our model would interpret. We size them down so we could properly process them. This is an example of some of the written numbers in there. We have 60,000 different images that the model will be trained on, and 10,000 that the model will be tested on. And just some more examples of images. So here's a 5. As you can see, it corresponds to the 0th point of the training images. Now, to define our model, we get a set of different layers. So at first we flatten the image for it to become a 28 by 28 array, and then we turn it into a 1D array so the next layer could process it efficiently. The next layer, which uses an activation of ReLU, creates a layer with 128 densely populated nodes, as described here. And each node, and densely populated means that each node at a layer is connected to every other node at the next layer. And then ReLU and softmax are both higher order functions, but we'll describe that later. And then in the next layer, through some probabilistic operations, we perform like a best guess of what something might be using softmax. And then once we compile the model, we use an atom optimizer, which uses that the very same calculus 1 optimization problems that the class likely experienced at some point, but expands this to a much larger extent using tensors. After that, then we train the model. We define it to train on 3 epochs. If you train on any more, there could likely be a result of overfitting, where if we were to test on a completely new data set that the model has not experienced, it might actually lose in accuracy. So then once we test it, once we train it, we then test it, and here's like an example, or like here's where our accuracy was once we tested it, but just for demonstration purposes, we'll run it again. And we got 97.46, which I consider pretty good, and for just a couple lines of code using TensorFlow, we got it recognizing handwritten numbers. So going back to our presentation. So as you saw from our demonstration, we had several layers, and I mentioned that we wouldn't go over ReLU and softmax. So ReLU is basically a function that can be described as the max between the input and 0. So if the input is a negative, it returns 0, else it returns the value itself. And this can basically help in determining which input values get progressed forward off of probability and stuff like that. So softmax is then a function that converts vectors of values into probability distributions, which are used in the end to determine whether something is what the model expects it to be. And these relatively basic functions through higher orders get applied to different nodes and layers, where these functions can help decrease the amount of code you have to write and overall make it more readable to the user.